When the James Webb Space Telescope finally saw the edges of the universe, we knew we had a problem. Webb was able to resolve light emitted from stars 13 billion years ago, helping us to peer back in time to some of the universe's earliest moments. But what we saw was not a sparsely populated proto-universe where matter was only just starting to coalesce into the first tiny, intermittent galaxies here and there. The early universe was a bustling place. It had galaxies, too many of them. They were too bright. And the black holes we started to spot in their hearts had grown too big, too quickly. Some began to proclaim that our models were wrong and cosmology was in crisis. But in a strange twist, one of the most resilient mysteries in all of this might be about to unravel thanks to a black hole with an impossibly big appetite. Its name is LID 568, and we've just seen it breaking the Eddington limit, and it might just be the key to everything. I'm Alex McColgan, and you're watching Astrum. Join with me today as we explore LID 568, the Eddington limit, and its groundbreaking implications on cosmology. A black hole breaking physics? By now I really shouldn't be surprised. It takes time to cook up a galaxy. Interstellar gas and dust need time to subtly come together under gravity until a critical mass is reached and stars start to ignite. These stars live and die, and from their deaths new stars are formed. This too takes time. Cosmologists have observed our universe and, based on what they saw, created models for how old our universe is and how quickly galaxies form, which is why the JWST data caused such a crisis. Things were not as the models predicted. Fortunately, some of those problems proved solvable in the months after the data was released. For example, the brightness of the galaxies we could see through Webb. This brightness implied that there were far too many stars present in those galaxies. So many stars should have taken much longer to form. And yet there they were, fuzzy red dots at the edge of Webb's resolution. However, scientists at the University of Texas studying Webb's Cosmic Evolution Early Release Survey realized there could be another explanation for all that excess light. And, counterintuitively, that explanation was black holes. If we work under the assumption that there were massive black holes in these galaxies, rapidly consuming cosmic gas, then the intense friction given off by these hungry leviathans as they ate created an excess of light in their accretion disks. This explains why the galaxies overall seemed brighter and were throwing off our estimates. Once you add these shining black holes, you don't need so many stars. The mass of each problematic galaxy dropped, and everything fell back into line with the cosmological model. Problem solved. That reinforced how important black holes are to our understanding of the early universe, which was in and of itself a problem because the black holes themselves broke our models too. In particular, cosmologists struggled with the thorny question of how they'd come to be. For small black holes known as stellar black holes, there was no issue. Stellar black holes have masses a few to 100 times that of our Sun, and we understand very well how they are formed. They are the collapsed remnants of a sufficiently massive star, and there would have been time for such black holes to form in the early universe. But scientists were struggling with the supermassive black holes, with masses tens of thousands to billions of times that of our Sun, which tend to lurk at the central point of galaxies. And due to something called the Eddington limit, there just shouldn't have been time for these kinds of black holes to have formed where and when Webb saw them. And yet, there they were. And they were numerous. In 1920, an English astronomer and physicist called Arthur Eddington formulated the idea that there was a limit to how quickly either a star or a black hole could grow. This was because photons carry momentum, a tiny amount, true, but enough to exert a push. This is what pushes solar sails on certain hypothetical spaceship designs, that tiny amount of momentum imparted by photons. For mass to enter into a star, it has to push against a constant stream of photons that are radiating outward, and at a certain level of brightness, not even gravity is strong enough to pull against the flow. This is called the Eddington limit, and stars that brush against its boundaries, such as Wolf-Rayet stars, bright stars 20 times more massive than the Sun, emanating powerful stellar winds, are just the slightest nudge away from blowing themselves apart. For black holes, you might think this would be less of a problem. Isn't the whole point of black holes that they don't radiate any light? But their accretion disks are a different story. As we discussed earlier, accretion disks around supermassive black holes can be incredibly bright, particularly around supermassive black holes, sometimes dwarfing the brightness of the stars in the galaxies they reside in. With brightness comes resistance to gravity, and black holes have to obey the Eddington limit too. So even though given enough time and mass, stellar black holes could theoretically grow into supermassive black holes, it doesn't seem plausible that this actually explains all the supermassive black holes we see in the early universe. Simulations have been run, and although it is technically possible to grow a stellar black hole into a supermassive black hole in that time frame, it would require those black holes to be feeding at near the Eddington limit non-stop since their birth, which just doesn't happen. Black holes in real life often run out of mass nearby and need to wait to run into more, or for more to come to them. To further complicate the matter, we're not completely sure that supermassive black holes are the grown-up version of stellar black holes in the first place. Supermassive black holes are common at the center of galaxies, and there are thought to be 100 million stellar black holes in our Milky Way alone, based on the number we've seen. But intermediate black holes are suspiciously lacking, with only a handful of potential candidates. You would think we'd see a lot more. Struggling for certainty, scientists began to hypothesize that supermassive black holes were instead born in some other way. Many cosmologists have been exploring the idea that because everything was much closer together in the early universe, things might have been dense enough that interstellar dust itself could conceivably have collapsed to form a black hole directly, skipping the star step altogether. If this is true, and there is some evidence to support the theory, then perhaps supermassive black holes were once capable of simply being born that size or near it right from the offset, even if such a thing is no longer possible in our more spread-out universe today. But this is by no means certain. Scientists might be able to find the answer to this cosmic mystery, but the number of NASA scientists is dropping. Nearly 4,000 NASA employees have recently quit, likely due to budget cuts, which is a big blow to science. I checked Ground News, today's sponsor, to see how different outlets were covering it. For this story, while concern for NASA cuts is bipartisan, left-leaning outlets are more likely to highlight that NASA's cuts are coming under heavy criticism, while the right is more likely to soften the blow by using terms like early retirement. This is why Ground News matters. It pulls articles from across the political spectrum so you can compare coverage and spot bias. They also show you who's paying for the news and even how factual their reporting is, providing vital context. If you want a more balanced view of important issues like this, scan my QR code, go to ground.news/Astrum, or click the link in the description. You'll get 40% off their Vantage subscription for unlimited access. That's just $5 a month, and it helps support the channel. Data was starting to suggest that black holes appearing directly from the interstellar dust might be the answer scientists were looking for. Then LID 568 came onto the scene, and the pendulum swung the other way again. LID 568 is a very distant black hole between 12.1 and 12.3 billion light-years away. It's so far away from us that we can't see it at all using visible light. The expansion of the universe has redshifted it all into infrared ranges. But even its infrared emissions were too dim to be picked up by heavy hitters like Hubble alone. It took the Chandra Cosmos Legacy Survey's combined telescopes and the incredible resolution power of the James Webb Space Telescope to see it at all. Even then, LID 568's whole galaxy is little more than a faint, red and compact dot. But the light emissions from this red dot are revealing. X-rays given off by LID 568's accretion disk reveal that it was actively consuming matter in its galaxy's heart in a way that no one expected. You see, LID 568 crucially breaks the Eddington limit. And not just by a little, it's 40 times over the accretion speed limit. It is well on the way to having its license revoked. How is this possible? It turns out that breaking the Eddington limit is in fact possible, but only for short bursts or in sneaky ways. For example, jets can help you get around the Eddington limit if all your photons are being blasted off in a single concentrated direction. All the other directions can eat to their heart's content, with no photon feedback getting in the way of a good meal. There are other possibilities. While Eddington's limit says that once the brightness of the accretion disk becomes too high, all the black hole's food will be blown away, There is a period of time before this happens where a greedy black hole can snatch at the escaping matter and potentially enter super Eddington territory. Like an overeager diner, it might pay for it later, but for a short burst that level of accretion can occur. If this is true, it might just explain how supermassive black holes in the early universe came to exist, and certainly Lid 568 exists, and is the clearest example to date of a black hole accreting this quickly. That demands our consideration. Much like the impossible supermassive black holes themselves, they are there. It's now our job to attempt to understand how that's possible. So mysteries remain. If Lid 568 is accreting matter past the Eddington limit, it proves such a thing is possible. But what of the other strange things JWS saw? Where are the intermediate black holes that stellar black holes ought to grow into, on their way to becoming supermassive? Why are there so many galaxies in the early universe, more than our models should allow? Do direct collapse black holes, ones formed from the cosmic dust itself, with no stellar intervening step, really exist? Our models might be on the right track, but something is missing or incomplete. Black holes exert a phenomenal influence on our universe, and there are secrets surrounding them that they guard jealously. As powerful as the JWS is, it has not allowed us to crack this mystery, not yet, but then perhaps we ought to be pacing ourselves. Thanks to our telescopes, we have seen billions of trillions of stars. That's a lot of data. Accrete too much information all at once, and it might prove difficult to absorb it all, so says Eddington, and his rule is never to be broken, except of course when it is.